Hi everybody, this is Mr. Folly, and hopefully this will be a happy new podcast on New Computer. Looking at podcast 2.3, periodic table trends. All trends are due to size, nuclear charge, and maybe shielding. Electronegativity, we're going to find out the definition, the equation, the trend. Ionic radius, again, definition and trend. And then ionization energy, I should have written that down, ionization energy. And then we're going to do exceptions for Excel only, and then prep the step a little earlier. So let's take a lookie. Actually, we're not going to do the exceptions now that I think about it. Explain the main way atoms differ, and you just explained every trend. So the main way they differ is size. Bigger is less attractive. High school, romances don't last through college. So if you're far away, it's less attractive. So if you go to school in lovely University of Alabama, and your little sweetums goes to school at Stanford, you're very far away. And it's like, oh, you're wonderful, I love you forever. But then what happens? Well, there's somebody that happens to be at your university and happens to be at their university. And what happens? And you're broken up by Thanksgiving, okay? Which, of course, is the most stable day of the year in America. High school romances don't last through college, do that. Nuclear attraction. So what this means is more protons means more attractive. Like more money. If someone has more money, yeah, they're more attractive. If all other things are equal, dollar bills, y'all. You people are awful. Okay? So bigger is less attractive. So that means smaller is more. It's easier to be friends with somebody who's close to you. Smaller is more attractive. And more protons means more attractive. And then we'll talk about shielding. Shielding, inner electrons make a nucleus less attractive by blocking the attraction. So if this is my positive nucleus, and I'm an electron all the way out here, what I have is we'll Bohr model this one, layers of negativity that repel this poor electron. Okay? The electron is attracted to this nucleus, but the more layers of repulsion, the less attractive they are. So this would be if you're really interested in a girl, and this is her big brother, big beefy brother, and then big intimidating father, and then the mother with a gun. So they're a little less attractive because they scare you more. So include these three things. So include what three things? Size, nuclear attraction, and shielding. So the answer for every one of them is applying size, nuclear attraction, and shielding. Whoops, I lost electronegativity already. Electronegativity is the ability to attract electrons in a bond. Okay. So the trend fluorine is the Mac Daddy. So remember, you've got a periodic table. Get out your periodic table. Looks a little something like this. Whee! Here's fluorine. So fluorine is the most attractive. Why? Because as you go this way, fluorine is the smallest. As you go this way, it has the most protons, so it is more attractive. Right? Don't do that. As you go up, remember these guys have a bunch of rings. This guy only has, honestly, 2. Right? So as you go up, it is smaller. So it is more attractive. That's why fluorine is the Mac Daddy, the most attractive in a bond. Francium is the opposite. So francium is down here. Okay, if you look at your periodic table, it's right there. Why? Fluorine is small and attractive because it has so many protons for its row, so it will be able to attract bonded electrons easily. This is the whole answer, right? Now, francium is a big loser. So francium is a big loser. Those of you who are taking European history will find out this is often true. Francium is down on the bottom. Remember, you get bigger as you go down the bottom, right? And francium, because it's so big and its nucleus is the smallest, so the fewest protons in its row, that means it is a big, unattractive loser. So if electronegativity is the ability to attract electrons, and fluorine is a big, unattractive loser, fluorine is bad at it. I'm sorry, not fluorine. Francium is bad at it. Fluorine is good at it. Why? Fluorine is small and attractive because it has so many protons. Francium is big and fewest protons per its row, which makes it unattractive. Ionic radius, this is the size of an atom. Cations get smaller. Why? They lose an entire energy level. So if I have calcium, let me just hop back to one. I didn't. Okay. So if I have, whoops. So let's say I have potassium. Potassium, I think, is something like 3s1 or whatever it is. Potassium ends in s1. If potassium loses an electron, that whole energy level is gone. So here's my nucleus. And if I'm a metal, oh, can I erase? Oh, I wonder if this will erase. It does not. Oh, man. Eraser. Yeah. So if I have 2, 8, and I have 1 electron here, notice if I lose this 1 electron, because cations are positive. Oh, I forgot to say, cations are positive electrons. Okay? And the reason why I remember cations are positive electrons, this is my picture of a little cat, because little teeth, fangs, cats have paws, right? So cations are positive. So if they're positive, they lose an electron, so they would lose an entire energy level. Oh, come on, give me my eraser back. So what happens is if you lose this 1 electron, you get smaller, and thus you're more attractive. That's why they get smaller. Oops. Anions get bigger. Why? So in the same setup, so if I go back to this spot, ooh, no. Oh, no. If I go back to this setup, and I have 6 electrons, and then I add more electrons, so if I have, whoa, that zoomed in. I did not want to do that. That's okay. Yikes. I don't have my pen anymore. Uh-oh. Don't do this to me. How do I get it back? Oh, well. Maybe if I change slides. That won't work. So I guess I'm going to end this podcast because I don't know how to use my computer yet, and I'll pick it up with a part 2. Toodles.